Okay, so as motivation for the acceleration field, I'm going to draw the little nozzle that you just saw in your quiz. Right, if you have a converging, diverging nozzle that has flow entering here and exiting here, we know from our discussion of we know from intuition as well as our discussions from the last from chapter 3 that this wide region, is going to be a region of relatively low velocity. This region here is going to be relatively high velocity, and this region here, once again, will be relatively low velocity. All right, so intuitively, we can recognize that the particle that travels from the top to the bottom is itself going to begin moving slowly. It's going to experience an acceleration that speeds it up, and then a deceleration that slows it back down. All right. This is somewhat at odds with the idea that if we were to put a probe right here, right near the neck where it begins to narrow into that constriction, say point A, or we'll just call it P for probe. If we were to observe point P, let's turn off that. So observing point P, the flow will not change. This is an assumption. In other words, we're stating that it is steady in an Eulerian sense. However, at the same time, every particle that passes through point P is itself experiencing an acceleration as it begins to move from that low region to the high velocity region. So these are the two ideas that we want to reconcile. So the tool that we're going to develop to reconcile these two ideas between the Eulerian steadiness of a flow, even when there's Lagrangian unsteadiness in that flow, is this thing called the material derivative. And it's going to enable us not just to talk about velocities, but also things like temperature, salinity, any properties of a fluid. Now, why? Okay, the question is why do we need to expend this effort on moving back and forth between these two ideas? And the answer to that is, we showed last time, that we like to work with these things called velocity fields or field representations. However, some of our very familiar laws of conservation, such as Newton's second law here, F equals ma, these are meant to apply to individual Lagrangian particles. Okay, the force on a particle is equal to its mass times its acceleration. It itself is not, how do you apply F equals ma to a position in space? Right? It's a kind of a weird concept. And the answer is that we want to be able to write this A term, this acceleration term, as a field as well. In other words, we want to write the Lagrangian acceleration using an Eulerian representation. There's a lot of back and forth, but it makes things a lot easier mathematically. So F equals ma, and other conservation laws are written for Lagrangian representations. And we want to apply them using Eulerian representations. All right, so the acceleration field we've already established, that here, the first step here is we've established that the velocity of a particle A can be written as VA, right, as velocity is equal to really VA is a function of that particle's position and time, where RA is equal to XA I plus YA J plus ZA K, right? So that's its vector position. So naturally, right, if we're writing the acceleration of this particle, we're just going to be taking the time rate of change of its velocity. So A of A is going to be written as d dt VA. Okay, so if we're taking the time rate of change of something that is itself a function of time, right, then by necessity we have to apply the chain rule. So digging back into our calculus, application of the chain rule is going to give us A is equal to d dt of, well, let's say, let's split this into components. So we'd say d dt of UA, right, t I plus VA WA Okay, so U, V, and W are respectively the X, Y, and Z components of the velocity of particle A. All right. And so all we're saying here is, let me go ahead and put that in square brackets. I'm missing. There we go. We're taking the time rate of change of the velocity vector. So writing this now in component form with the chain rule applied, we would get leave a step out in here. No. I see. I did it. Let's do first just the x direction. That is, we're going to concentrate first on the x component of the velocity and its time rate of change. So we would say that the x component is equal to, right, d dt of u a r t d dt of x ua times dx dt plus dy ua dz Alright, so because R itself, right, it involves the x, the y, and the z coordinates of particle A, we're applying the chain rule to R. We're saying that the time rate of change of u is equal to the time rate of change, or the rate of change with x of u times the time rate of change of x. And we're doing this with x, with y, with z, and then finally, because u is also a function of time itself, take the time rate of change of it itself. So each of these terms, right, dx dt, dy dt, and dz dt, are themselves velocities, right? The time rate of change of the x-coordinate, y-coordinate, z-coordinate. We would write this as UA, VA, and WA, the x, y, and z velocities. So we can write this in a more compact form, saying that this is equal to UA dUA dx plus VA dUA dy plus WA dUA dz plus time rate of change. Okay, so this gives us the x component of the acceleration, and this is where I want to point out these different terms we have here. So these first three terms, right, where it's a spatial rate of change times a velocity, these are what we call the convective acceleration terms. And then this term right here is what we call the local acceleration. The idea being that the local acceleration is the actual change in the velocity field with time. So if you have a velocity field that is Eulerian unsteady, something where it's got a t explicitly in the expression for the velocity field, that's going to show up in that du dt. But if you're Eulerian steady, as in the case of our converging, diverging nozzle, right? What this first convective acceleration term tells us is that there's going to be acceleration experienced by the particle because it itself is traversing a spatially non-uniform velocity field. So it has to go from those regions of low velocity to high velocity back to low velocity. So we can do the same thing, right, with the, so this is the x component. We can do the same thing with the y component and z component of the accelerations. I won't belabor those points, but I'll just write them out briefly. So a y, right, ddt, va, which is, I'll write this one out slightly differently. ZAT. So same idea, but now I've taken these x, y, z and split them out so it becomes a little more obvious that those make up R. We would write UA dVA dx plus VA dVA dy plus WA dV dz plus dVA dt. So, and then the y component would be the same thing, except, right, the arguments of each of these derivatives would change from v to w. So this v, that v, and that v. But these terms here would remain the same. So let's sum it up. The idea here now is if this applies to one particle, A, we haven't specified what particle it is. We just said take a particle, name it A, write out its acceleration in terms of the field representation of its velocity. We could apply it, if to this particle, to any particle. So let's drop the subscript A, and we'll go ahead and write it in its full vector form. A is equal to d t plus u du dx v y plus w du dz. T plus v dx plus W dv dz. Okay, so if we write out the x component, y component, z components on these three separate lines, we can start to see the pattern that develops, right? So in the beginning here, these first terms, I reorganized, so now these first terms are our local acceleration. And we have our convective accelerations. Where, again, this local acceleration can be thought of as our temporal or our time variation. And this here is our spatial variation. And again, come back to our basics, this here represents Eulerian unsteadiness. And this here represents purely Lagrangian unsteadiness. So those are the interpretations of the local and convective acceleration components. This seems like a mighty complicated way to write out an acceleration, but it's really quite formulaic. All right, you'll notice that along the top, or in each column, right, or in each row, the arguments of our derivative are the same. Across the top, the argument is u. Across the middle, it's all v, and across the bottom, it's all w. So this, right, suggests that there's some sort of pattern to this expression. And in fact, we would write that more compactly using this right here, d dt v, which is dt plus a b dy w d dz. Okay, so what we've done here is we've said we're going to treat these derivatives as operators. Okay, we're going to treat them sort of like variables, but instead of multiplying in, what they're doing is they're operating on whatever they get multiplied with. So, right, the time rate of change, the convection through the x rate of change, convection through the y rate of change, convection through the z rate of change, all times the velocities x, y, and z. And this is actually something that we call, this expression right here is what we call the material derivative. So d dt, or this big D dt, is our way of expressing material derivative is a way of writing the Lagrangian rate of change of a variable. And it applies to more than just the velocity, right? This example or this brief derivation that we did was completed in the context of applying it to the velocity field. But in fact, the variable that we're tracking the rate of change of can be any property of a fluid. It can be velocity, it could be density, it could be temperature, salinity, etc. This is simply a way of tracking the rate of change of each particle at its instantaneous position in space. A few more formalities here, and then I have a couple examples that should help firm up this idea and show you how to apply this because it's a somewhat abstract idea, but it's actually very useful. So the dt, right, as an operator can be written in vector form as follows: ddt plus v dot product with the gradient operator. All right, and before we start panicking because now we've got vector formulations in here, recognize that all this is doing is it's saying, right, the dot product. The x components of the two multiplied together, added to the y components of the two, multiplied together, added to the z components of the two, added together. So if we've got v, right, this is u I plus v j plus w, okay? And our gradient operator, right, is a way of writing the rates of change in x, y, and z, but each one assigned a unit vector. Okay, so if these are our vector representations of those two, v and grad, we simply multiply these two guys together, multiply these two guys together, multiply these two guys together, and add them all up. And what we get is that expression up above that's expanded out. And once again, we would call this our local rate of change, and we would call this term here the convective rate of change. Yeah.
So about the local rate of change, wouldn't the use of the gradient operator imply, because we have v as a function of u and v and w, and u and v and w in turn are functions of x, y, z, and t, then the gradient would have a term dv, dt, dt, dt. So you wouldn't need actually the partial.
Saying if so, you're saying that because u, v, and w are
functions of x, y, z, and t.
Right. So because so that's you are correct there, except for the fact that the chain rule is already accounting for that. Because if u, v, and w, right, what do those make up? Those make up v, the vector field v. And so the time rate of change of v is like that's how we're taking the time rate of change of v is through the chain rule, where we take ddt as a partial derivative of v. We account for the time component of the rate of change, and then we step through each of the spatial components of the rates of change. So, I guess are you wondering about the fact that we have x, y, and z?
No, I'm wondering about the fact, like when you use the gradient operator,
yes, we
don't actually need the term partial dt, like ddt.
Oh, well, the gradient operator doesn't include any time derivative in it. There's
going to be a term like dv dt, 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 and you're going to cancel the dt equals 1. So
dv dt. Let's chat after class, but I think the thing is the definition of the gradient operator, right, is that it's just spatial. It's partial derivatives with respect to x, y, and z. There's no time in there. If you want to account for the chain rate of change, you have to include it elsewhere, which is why that partial with t is coming in. Okay, so quick little extension, and then we'll get to those examples. So the idea is, now if we want to apply it to something other than the velocity, we would write it more formally as, right, dB dt is now equal to dB dt plus grad times v of b, where b is any property that can be a scalar, vector, tensor, etc. of the fluid, but B must have B must be written as a field in order for this to apply. All right. So let's consider a qualitative example first, and then a more quantitative one. So let's say we've got let's say we've got a river that has a velocity field written okay, so because we have the x, y, and z, it's written as a field representation. Let's say we've got u, a vector, as a function of t only, which is the velocity of a fish, right? Written relative to Earth. And then we have f, x, y, z, and t, which is the dissolved oxygen concentration in the river, written as a field. So symbolically, how would we write out the time rate of change of dissolved oxygen encountered by the fish encountered by fish eggs stuck in the rocks at the bottom of the river. In other words, ones that have zero velocity. And encountered by fish eggs drifting with the current. So take about 2 or 3 minutes here and go ahead and talk amongst yourselves. Get pointers from the guy sitting next to you, and see if you can come up with the expressions in terms of v, u, and f that we would use to write out each of these terms.
Change it.
Anyone want to start out with volunteering the time rate of change of dissolved oxygen seen by the fish that's swimming through with that velocity u? Right, so we would write df dt, right, fish is equal to what? How would we write this out? First term, think local rate of change. What variable is going to go into that operator? Good. df dt, right? That's the time rate of change of the dissolved oxygen throughout the river. Okay, so obviously if the fish is in the river, it's going to experience that. Plus, what would our convective term involve? We can go ahead and write it in a vector form. What? We've got our gradient operator dotted with what?
Isn't that a u for the velocity of fish?
It's going to be u, right? Why isn't it v? Any ideas?
Because it's relative to the curve, so it already includes that.
That's correct. Another way of thinking about it is, right, if, or to maybe state it a little more simply, the fish's velocity is irrespective of the river's velocity, right? We've established that F is a field of oxygen concentration in an Earth-fixed frame, and so regardless of how the river's flowing, we care about how the fish is moving through that field. And then F here. Okay, what about the eggs that are stationary? Local rate of change going to be the same as that experienced by the fish. Now, what's our velocity in this case going to be? 0, right? Because it's not moving through that spatially varying field. So the only rate of change experienced by a point fixed there is going to be the time rate of change of the oxygen concentration, that local time rate of change. And then finally, eggs drifting with the current. Again, same local rate of change. And what are we going to put in here? V, precisely. Because now it's being carried through that spatially varying field by the river's own velocity. Okay, we're going to end it there. I've got one more example with hard numbers that I'll go ahead and work out and post on Icon so you guys can look at that. And I'll see you guys tomorrow evening at the review session.